Okay, now we're going to do the second gas law, which is called Charles' law or Charles's law. And this one is on page 106 of your textbook. And Charles' law shows the relationship between volume and temperature. Now, it's not volume and pressure like Boyle's law, it's volume and temperature. Okay, now Charles' law, the whole definition of it is the volume of a fixed quantity of gas is directly proportional to temperature in Kelvin if the pressure is constant. Now, there's a lot of new things that you're going to encounter here. First of all, they're telling us volume and temperature is directly proportional. Okay, and the pressure is constant. Now, if you remember Boyle's law was volume and pressure is inversely proportional when temperature is constant. But since Charles' law is dealing with volume and temperature, now pressure is constant. Now, the catch is that volume and temperature is only directly proportional to each other if the temperature is measured in Kelvin. Now, what is Kelvin first of all? Now, Kelvin is just another kind of unit to measure temperature. Just like how you can measure length, for example, in many different ways. You can measure it in meters, centimeters, kilometers, yards. There's many ways. Same with, for example, pressure. You can measure it in pascals, atmosphere. Now, temperature can also be measured in many ways. One of the ways which you used to is in degrees Celsius. And now, when we're dealing with gases, we measure temperature in Kelvin. And Kelvin is showed with a capital letter K. Right, so Charles' law, it states that volume is directly proportional to temperature only if the temperature's units are in Kelvin and the pressure has to be constant. Now again, like with Boyle's law, please learn this definition as is and do not forget to mention that pressure must be constant, otherwise you're not going to get full marks. Now, how do you change degrees Celsius to Kelvin and the other way around? Because if we need to get Kelvin, we need to know how to convert temperature into Kelvin. And it's very simple. If you have temperature in degrees Celsius, all you need to do is add 273 to it, and this will give you temperature in Kelvin. So you're just adding 273. There's no divided by 1,000 or any of those things. You're just adding 273, and that will give you temperature in Kelvin. Now, when you're dealing with gases, you mostly need to know how to change degrees Celsius to Kelvin. But if they ever ask you to change Kelvin to degrees Celsius, it's just the opposite way. So instead of adding 273, you're now going to minus 273. Now, they are not going to show you or give you this in the data sheet or in the formula sheet. You need to learn it off by heart. All conversions, you need to make sure you know it off by heart before you write any test or exam. So again, to change degrees Celsius into Kelvin, you're just going to add 273. Okay, now from this definition, we come up with this formula, which is Charles' equation, and it is V1 over T1 is equals to V2 over T2. Now, can you see that it's similar to Boyle's law? You're also having two pressures and two volumes. Now, for Charles' equation, you have two volumes and two temperatures, but here they are divided by each other. So you're going to have the initial volume divided by initial pressure is equals to final volume divided by final temperature. And again, just like you have a constant for Boyle's law, for Charles' law, you also have a constant, and that constant is if you take any volume divided by the pressure, that will give you K, which is a constant. So it doesn't matter what volume do you divide, what that corresponding temperature, you will get the same answer. Okay, now, again, we said we always have graphs in physics because that's what we do in chemistry and physics. We always deal with graphs. Now, since we're dealing with volume and temperature, we're going to have two graphs. We can plot this in two different ways. Right, now if you look at this graph on page 106, you can see you have a graph here of volume versus temperature, but here temperature is in degrees Celsius. Now, if you went over the definition, you see that volume and temperature is only directly proportional if temperature is in Kelvin, not degrees Celsius. So if we plot this graph of volume versus temperature in degrees Celsius, can you see that we are getting a straight line graph which is increasing, which tells you that volume increases and temperature increases together. So they both increase with each other. But for something to be directly proportional, it has to go through the origin. So it has to go past 0. And can you see that this graph is definitely not going past 0, which tells you that volume and Celsius temperature is not directly proportional. Now, what is special about this graph is if you take this graph and you extrapolate it into the negative axis, you will see that the the x-intercept that you get when you extrapolate this graph will always correspond to the number negative 273. And doesn't a number seem familiar? It comes from converting degrees Celsius into Kelvin. So every time you have a volume versus temperature graph in degrees Celsius, if you extrapolate it, the x-axis will give you negative 273. And negative 273 corresponds to a temperature in Kelvin of 0 Kelvin. Okay, so negative 273 degrees Celsius is equals to 0 Kelvin. And what we call this temperature, which is 0 Kelvin or negative 273 degrees Celsius, it's called absolute zero. So if I ever say absolute zero or you ever read it somewhere, it means 0 Kelvin or negative 273 degrees Celsius. That is what we refer to as 0 Kelvin. Now, let's look at a practical example of how volume and pressure is related. If you look at this picture on page 107, can you see we have a whole lot of balloons here? Now, this balloons in the first picture is at room temperature. Now, room temperature, it's warm enough. It's about maybe 20 or 25 degrees Celsius, depending on where you are in the world. But can you see that the balloons are at room temperature and the balloons is inflated? It's like a normal blown up balloon and it takes up a lot of space. So the volume is greater because room temperature is high. Now in the second and third pictures, you actually have liquid nitrogen being used or being put close to balloons. Now liquid nitrogen, it's, if you know about it, it's very cold. It's almost like freezing something. So liquid nitrogen, it's cold, and if you have to put balloons in liquid nitrogen or close to liquid nitrogen, it's like putting it in a freezer. You're going to cool it down. And if you look at the third picture, can you see the balloons now shrunk? It shrank to such a small size because of the liquid nitrogen cooling it down. And this is what shows how volume is directly proportional to temperature. So if you decrease the temperature and if you make it cool, the volume of something is going to decrease and it's going to get smaller. Okay, now this section is another easy, nice section like Boyle's law. It's an easy way to get marks. All you need to know is the definition, which is volume is directly proportional to temperature in Kelvin when pressure is constant, and you need to know how to use these formulas. Now again, like Boyle's law, the units doesn't really matter, but because we're dealing with temperature in Kelvin, the units does matter for temperature. So for volume, you can use any units, centimeter cube, decimeter cube, meter cubed. As long as it's both the same for V1 and V2, it will cancel out. But for temperature, it's a rule, you have to use Kelvin when you are using any of these formulas. If you use degrees Celsius in these equations, you will get a wrong answer. So whenever you use Charles equations, whether it's this one or this one, you need to make sure that temperature is always in Kelvin. Always. This is a rule. So please don't forget that. Just, if I were you, you just always change things to Kelvin. Right, another important thing to know is you cannot get a negative temperature in Kelvin. So you can get negative temperature in degrees Celsius, but because you're adding 273 to it, Kelvin, you can't really get a negative temperature. Right, let's look at a few examples of how we're changing degrees Celsius into Kelvin. Right, so we're going to example 6 on page 108. Number 1 here, it says convert each of the following to Kelvin. So you have 37 degrees Celsius, and remember what we said, when you change something to Kelvin, all you're doing is adding 273. So we're going to say 37 plus 273, which will give you 310 Kelvin. Now, Kelvin temperature will always be greater than degrees Celsius. So if you work out Kelvin temperature, it must give you a higher number than the degrees Celsius. If not, that means you either minusing it instead of adding 273. Okay, so just remember, Kelvin will always be greater than degrees Celsius. All right, let's look at number 2. You have negative 20 degrees Celsius. Can you see it's a negative number, but it's degrees Celsius. But when we do it in Kelvin, we have to get a positive number. So you're going to take that negative 20 plus 273, and that will give you 253 Kelvin. Right, let's look at example 7. Now we're converting it to degrees Celsius, but it's not really necessary to know this because in formulas, you're mostly doing it the other way around. But let us just do it anyways. So you have 250 Kelvin, and if you want to change it to degrees Celsius, instead of adding 273, now you're going to minus 273. So you're going to say 250 minus 273, which will give you a negative 23 degrees Celsius. And can you see? Degrees Celsius can be negative, but Kelvin is not mostly likely going to be negative. Okay, number 2, 90 Kelvin. So again, to change it to degrees Celsius, you're going to say negative 273, and that will give you minus 183 degrees Celsius. Now, this is very simple, but if you leave out the step of converting temperature into Kelvin in your equations, you will lose a lot of marks. So even though it is simple, this is the way they trick you. So please just remember, temperature must always be in Kelvin. Now, again, from the first section, which I told you to summarize, when you have a real gas, it always deviates from ideal gases at a low pressure temperature and a high pressure. Now, since we're dealing with Charles' law, which involves temperature, if the temperature is too low, a real gas is going to go or deviate from ideal gas behavior. So if we are drawing this graph of volume versus temperature in Kelvin, can you see it's a straight line through the origin, which tells you that volume and temperature is inversely proportional to each other only when it's in Kelvin. But if you have a real gas, which means it's not going to follow ideal conditions, it won't give you the perfect graph that you want, because now the conditions are going to be different. Okay, now don't worry too much about that. Let's go straight into examples. Okay, example 8. The diagram shows a gas syringe with a maximum volume of 150 centimeter cubed. The plunger of the syringe can move freely 120 centimeter cube nitrogen gas at atmospheric pressure and a temperature of 27 degrees Celsius. Now already when you're reading the question, you should keep in mind that we always want Kelvin temperature. So if you see degrees Celsius, make a note that you need to convert that as soon as possible. Okay, the syringe is placed in a warm bath of 77 degrees Celsius. So again, we need to change this. Calculate the change in volume of the nitrogen gas in the syringe. Now, obviously, there is only one formula you're going to use, which is Charles' law. Can you see they're giving us 2 temperatures and 1 volume, and they're asking us for another volume? So there is no other formula besides Charles' law. So can you see how simple it is? All you have to do is pick the correct formula, substitute, and that's it. Okay, so V1, they gave it to us, it's 120 centimeter cubed. So you're just going to put 120, and the units for volume doesn't really matter. We only care about the units for temperature. Right, now if you thought 150 centimeter cubed was the volume, just read the question again. It says here, the syringe has a maximum volume of 150. They didn't tell you that is the volume. They just said that's the maximum it can take, but it doesn't mean it's really that amount. Okay, so 120 is the actual amount of volume. Right, and then T2. Now T2 is 77 degrees Celsius. Now remember, we cannot use degrees Celsius. You can never ever use Celsius temperature in any of these formulas. So you need to change this to Kelvin. Now you have 2 options. You can either change degrees Celsius to Kelvin before putting it into the equation, like how they did it here, or you can just do it in the equation in one step. It doesn't really matter as long as you change it. So here they did it first. So you have 77. Remember, in Kelvin you adding 273, and that will give you 350. So that's that 350 here. And then you're dividing it by T1, which is 27 degrees. And again, you have to change it to Kelvin. So you're going to add 273, and that's that 300 here. And that will give you 140 centimeter cubed. So the most important thing to remember is with Charles' law, you just need to convert temperature into Kelvin by adding 273. Okay, let's look at example 9. A fixed mass of gas occupies a volume of 45 centimeter cubed at 100 kilopascals and 27 degrees Celsius. Now remember, Charles' law, we don't really have anything to do with pressure, so this is just to confuse you and to tell you that pressure stays constant, because that is what Charles' law means. Right, so we have volume. That's the first volume, and they said 27 degrees. That's the first temperature. Now, please remember, if you get confused, rather convert it same time. So there they converted it. 27 plus 273 will give you 300 Kelvin. Then they say the volume of gas is increased to 80 centimeter cubed, which means it was 45, it increased to 80. So that's obviously going to be V2. Right, calculate the increased temperature in degrees Celsius. Now they're asking you for temperature in degrees Celsius. But just remember, in formulas, we use Kelvin. So if they want the answer in degrees Celsius, we're only going to do that afterwards when you are finished using the formula. Okay, let's go straight into the formula. So you have Charles' law, V1 over T1 is equals to V2 over T2. V2 is going to be 80 centimeter cube. You're just going to take it directly. T1, it's by adding 273 to 27, so it's 300, this number here. V1, they gave it to us, it's 45, and then you're going to solve for T2 and you get 533.3 Kelvin. Now, if you're using this formula, it means you have to use Kelvin temperature in the formula, and your answer will also be in Kelvin. So if they're asking for you to give it in degrees Celsius, you need to take this Kelvin and convert it to degrees Celsius, and you do that by minusing 273, and that will give you 260.3 degrees Celsius. Now just remember, this formula will always give you an answer in Kelvin. So if you want degrees Celsius, you need to do this extra step. Do not ever think that this answer is in degrees Celsius, or that you should use degrees Celsius in this formula, because it's going to totally be wrong. Okay, right, let's look at the last example. Example 10. A fixed mass of a gas's volume is measured at 35 degrees. So again, can you see we have degrees Celsius? They will always give you degrees Celsius, because that's how they're going to trick you. So you just go straight away and convert it to Kelvin, and this will give you 308 Kelvin. Right, in a pressure of 1 atmosphere, we don't really need to know the pressure, but they're just telling you that it's constant. To what temperature must the gas be cooled to half the volume of the gas if the pressure is kept constant? Now in this example, they are not telling us the actual amount of volume. They're not giving us an actual value. All they're telling you is what the temperature will be if you half the volume, which means in the beginning you had volume, and then at the end, whatever your volume was, it's now half of it. Now, you know, in maths you use equations, you use x and y and z. You don't need to have an actual number. You can work out answers without having an actual value. So you're going to use Charles' formula. And now, instead of having V1 and V2, we don't need to have numbers. All we know is V1 is V1. It's whatever it was. And then they said it halved afterwards. So whatever V1 is, V2 will be half of it. So we're going to keep V1 as V. And then for V2, we're just going to call it a half V, because it just became half. So you don't need to actually have values. You're just going to put the ratio of whatever it changed by. Right. And then T1 is from here by changing 35 and adding 273 to give you 308, and that will give you 154 Kelvin. So do you see? Don't think there's a mistake in the question because they didn't give you volume. All you need to do is use ratios and you will get the answer from it, just like a normal equation.